Welcome to the editorial of the fourth mock internship test. Let's start with the first problem. So, we're given an array of integers a1, a2, and so on till an, and we're given a value k. The power of a number is defined as the number of ones in its binary representation. For example, let's find the power of 13, which is 1, 1, 0, 1 in binary representation, and this has 3 ones. So the power of 13 is 3. Because all we care about is the power of each element in the array, we can just replace each element by its power. Say our array is 13, 8, and 5. 13 is 1101, 8 is 1000, and 5 is 101 in binary. So the power is 3, 1, and 2. So we replace this array by this. Then we can use two pointers to count the number of strong subarrays. Say this is the array after replacing each element with its power. Initially, both pointers are at the beginning of the array. We then move the right pointer till we find the first element for which the sum is more than k. Since power values are non-negative, once the sum exceeds k, all the longer subarrays starting from that point will also have a sum greater than k. So we just add the difference to our answer. We then increment the left pointer, subtract that element from the sum, and then repeat the same process with the right pointer till the left pointer reaches the end of the array. Let's take a look at the implementation. I've used bit sets to convert each element into its power, and I've done this while inputting itself. This takes big O of n log n time and big O of n space for storing the array. It's n log n time because each conversion takes log n and there are n such elements. And this two pointer algorithm takes big O of n time because each pointer goes through the array only once and they move strictly towards the end of the array. That's all I had for this problem. Thank you.
Let's see problem B, temporal auction. The main idea behind the problem is you're given two sequences of bits from two players, Yukash and Varun, each of length n. They alternate placing bits. Yukash places the first bit, followed by Varun, then Yukash, Varun, and then so on. There's a special rollback condition. If Varun places a bid greater than Yukash's previous bid, and at least 3 bids have already been made, then the last 3 bids, 2 Varuns and 1 Yukash's, are erased. Your task is to stimulate this bidding process and return the final winning bid, that is the last bid remaining after all the rollbacks. Now, the main idea to solve this question is we'll be using stack to maintain the sequence of bits placed. This is because using stacks, we can easily remove the topmost bid and compare it to the other top bids that have already been made. When a rollback is triggered, that is when Varun's bid is greater than Yukash's bid, the top 3 bids of the stack are popped off. We have to ensure the stack has 3 bids firstly, then this is done. And popping off will also be very easy if we use a stack. We'll alternate between Yukash and Varun's turns as their bids are placed in the stack. This ensures that we have a clear idea of whose chance it is when a certain process is stimulated. So say, for example, Yukash's bids are given by Y1, Y2, and Y3, while Varun's bids are given by V1, V2, V3. For example, let's assume V1 and V2 are greater than Y1 and Y2, while V1 and V2 are less than Y1 and V2, while V3 is greater than Y3. Now, in a stack implementation, say this is the stack. Firstly, we'll place Yukash's bid and then Varun's bid. This will be done in one running of the loop. After that, in another loop running, we'll place Yukash's second bid, followed by Varun's second bid. What we can clearly see is that once the whole loop is run once, always Varun's bid is at the top. So this ensures that when we have to do comparison between Varun's current bid to the Yukash's previous bid, the topmost bid is always Varun's bid. This will ensure that we never take Yukash's bid for comparison. And it will also be easy in the popping condition that I'll tell. Now we'll place Yukash's third bid and Varun's third bid. We'll now compare Since the elements in the stack are greater than 2, we can do comparisons. We will compare in each case we'll do comparison, but I'm showing only for this case. We'll compare Varun's latest bid to Yukash's latest bid. If we'll see that Varun's bid is greater than Yukash's bid, in that case we need to pop back 3 elements. So we'll pop off V3, Y3 and V2. Since always Varun's bid was at the top when the loop ran once, this helps us in the popping of 3 bids ensures that we pop 2 of Varun's bid and 1 of Yukash's bid. Now, since there are no more elements present, we cannot insert any more elements in the stack, and the topmost element of the stack, that is Y2, is the answer, that is the winning bid. So moving on. While implementing this, we need to take care of few edge cases. First, one of them is running out of bids. We need to ensure that I and J are in the bounds when we insert them in the stack. We stack underflow. We need to ensure, firstly, we need to ensure that when we are comparing 2 bids, that is Varun's 1 bid to one of Yukash's bid, we need to ensure that the stack has at least 2 elements. Otherwise, upon comparison, it will lead to stack underflow. Secondly, we also need to ensure that when we do the rollback condition, the stack has at least 3 elements present in it. Also, we need to correctly identify whose turn it is to ensure that an alternating process of bidding is taking place properly. This is done by ensuring that once the loop runs, it's always Yukash's bid is placed and then Varun's bid is placed. So Varun's bid is always at the top when the loop is run. Now we'll see the code implementation of the idea. So we have a stack S. We initialize I and J variables, which are the indices of A and B respectively. We initialize them by -1 because we'll be incrementing them later in the loop. Since the stack is initially empty and none of these if conditions are held, I will be incremented to 0, and then we'll push Yukash's first bid in the stack, followed by Varun's next bid. Again, we'll run the loop. Now, since the stack size is greater than equal to 2, we have at least 2 elements present here to compare. One of Yukash's ith bid and Varun's ith bid. What we do is we take a variable Q and we take the topmost element of the stack. We pop the stack and then we take the second element of the stack. So this is P and this is Q. We further push back this Q inside the stack to restore the stack as it was. We have only done the popping thing to compare the 2 bits. Now, if P is greater than, if Q, sorry, my bad, this is Q and this is P. Now, if Q is greater than P, that is Varun's bid is greater than Yukash's bid, and the size of the stack is greater than 2, that is the stack should have at least 3 elements present to do the rollback condition. What we do is we pop 3 elements by using s.pop thrice. We pop 3 elements. Later we increment J, and if J is equal to N, in that case we break out of the loop because all the bits have been exhausted. Otherwise, we push back B of J inside the stack. This is because, as the question said, that once the rollback conditions are done, it is next Varun's turn to bid. So we are essentially placing with Varun's next bid here. Since the latest bid here would be Yukash's, which has to be followed by Varun's bid. We place by Varun's bid here and then we continue this loop. We break out of this loop once both I and J become greater than equal to N, since now all the bids of both the players have been exhausted. Now there would be a condition like, say, when there are 2 bids, Y1, Y2, Y3, 3 Yukash's bids, and V1, V2, and V3, 3 of Varun's bid. Excuse my writing. If we do this, if we implement the stack approach, what we do and say V2 was greater than Y2, in that case, we would pop off V1, V2, and Y2 from the stack. Then we would increment J and we would insert V3 inside the stack. Now there would be a condition that J would be equal to N, while I is still not greater than equal to N, since I is N minus 1. Like, this element is still left to be inserted inside the stack. So for this, to take care of this condition, we have this if loop, which ensures that we insert this y3 inside S, and then we break out of the loop, because now Varun cannot make any more turns since all his bits have been exhausted. Finally, we print S dot top, which is the latest bit that has been done. This would be our answer. The time complexity of the solution is O of n, since we are taking care of all the n elements at least once.
Let's now have a look at the third question. So we are given two strings A and B, and in a given operation, we have to remove X characters from the start of B such that the remaining string, that is that remaining suffix, is a prefix of the string A. Now, obviously, because each operation is going to cost you X square, we want to effectively remove smaller chunks at a time, right? As in, if you can remove 7 characters, it's always going to be better to remove 3 plus 4 instead of removing all 7 together because of the X square. So that means that we need to find all the suffixes of B that happen to be prefixes of A. And once you find all of those suffixes that happen to be prefixes, you will want to remove X characters in a way that you reach every single legal step, because the more legal steps that you can go through, the more intermediary steps that you can go through, the lesser your cost will be, because any double jump will cost you more because of the X square. Okay, so the question also requires us to solve this problem in either O of n or O of n log n or some other similar time complexity. So this is what we need to do. We need to find all the positions where the remaining part of B or the suffix of B is a prefix of A. And you can think about this problem for a while. You'll realize that there is really no easy greedy solution that you can apply, which kind of, I mean, there are greedy solutions, but all of them will be O of n square, which kind of forces us to go into DP. But if you are just going to be like storing a DP array that is just the booleans, like a vector of booleans saying, okay, this is a valid suffix, this is not, then what are you going to do DP on, right? You can't do any min or max operation, right? So this kind of leads us to the solution that we need to store some kind of number. And so that's how I'm kind of transitioning into this simpler problem first. So let's look at this simpler problem first. For every string S at every index, I will store the number of characters from that index forwards that happens to be a prefix. So this is the prefix and this is the number of characters forward from that point. Now you might think, okay, sure, this problem is fine, but how are we going to apply this into the original problem, right? And the idea here is, if you can solve the second problem, you can construct a string A plus any random character that does not appear in both like A or B, and you can just pass it to the second problem's algorithm. And what that will give you is, because now that for every single element in B, if you can calculate this, then you'll realize that if this I plus K happens to be the end of this merged string, then this left hand side is actually just the suffix of B, and this right hand side is actually the prefix of A. So this second problem will give us all the information we need to solve the first problem, right? But now you might ask me, okay, why is the second problem simpler than the first problem? Or why is this an intuitive solution? And there's no easy answer to that. The answer is, the second problem just happens to be a famous pattern matching problem, and there are known algorithms to solve this. And I acknowledge that if you don't already know the Z algorithm, or you don't know the KMP algorithm, this problem as a whole and finding this loophole is very unintuitive, and it's okay if you didn't get it. So that aside, let's now talk about how to actually do the Z algorithm. I hope I've convinced you that solving the second problem is sufficient to solve the first one. Let's get into how the Z algorithm works and how it does the second problem in O of n. Okay, so here's how it's going to go. I remember our goal: for every string at every index I want to find the max k such that this is holding true. Okay, so let's begin. So obviously, if you start from I equals 0, then you're obviously going to be able to match the whole string, because you can just put I equals 0 and you notice that. So for the first index, we'll just put n for the length of the string. Now from the second index onwards, I'll have to compare. So I'll compare A, and indeed they are the same. But if you see, B and A are not the same, so we only have a match of 1. So I'll put down 1 over here. Right, so that's what the question is trying to say, right? So from Si, just one index forward, or as in like one index is just itself, is matching the prefix, right? Now for B, obviously the first element here does not match the first element, so the answer will be 0. Then for D, it's going to be 0 again. Now here you'll see that A matches A, the next A also matches the next A, the next B also matches the next B, D also matches D. So we are getting, and then the next C is not matching. So we're getting 4, right? We're getting a match length of 4. But you might ask me, okay, fine, this is okay, but if you keep doing this for every single character, isn't this going to be O of n square again? Because for every single character, you have to, at worst case, search out for the entire string, right? So if this whole thing was just a whole bunch of A's, then you would see that this is n square. And that's where the optimization of the Z algorithm comes in. So I'll talk about that. So you saw that we had already matched this entire substring to this entire substring. That's great. But can we conclude anything about the remaining elements here? So if I'm talking about A, isn't this A just the same as this A? Like, think about it, because from here, that is, can I copy this number 1 over here? As in, without doing any more forward searches, can I directly copy the number 1? And it makes sense, right? Because from this A, I was saying, okay, there is only one character that's matching the prefix. And because the forward, like if you look forward from here, it's just ABD, that's the same as this. We have just matched it. Like, because in the previous step, we already matched it, we can say with confidence that this A is the same as this. And so you can actually just copy over the value of 1. And in a similar essence, you can copy over this 0 and you can copy over this 0 as well, right? Does that make sense? Now let's head over to C. So I'll just get rid of my scaffolding, and C again, you will check C with A. There's a 0 match, so we'll put 0. Then you will check A with A, it indeed matches. Next A with next A. Then there's a B that's matching. There's a D that's matching. And then you keep going and you notice all of this A, B, D is also matching. And we're getting a match length of, I think, 8. So we're getting a match length of 8. And again, if you were to repeat this, as in, because we have already matched this entire string, we can begin copying over elements. So this one can be copied over here because we know that it's the same thing. Then this B, similarly, we'll just copy over the 0. We'll copy the 0. We'll copy the 4. But now here's the question. Is this 4 actually correct? Right? If you notice, from this A, I was indeed matching 4 characters, that is AABD, and that is equal to the previous AABD. But if you see this A, there's a AABDA that is matching. So the answer is actually 5, right? It's not 4. And then you might think, okay, is my method wrong? Well, the thing is, if I here, because like, what is the 4 actually saying? The 4 says that there are 4 characters that matches, that is, these 4 characters are indeed matching the prefix, which is correct. But notice that in these highlighted segments that I had selected, that is this segment that I had selected from here to here, that is this match of 8 that I made originally, we had stopped at D. We haven't even looked at this element. So in addition to just writing down the 4, we'll have to scan out the next element, because we reached the end of our kind of range that we were talking about. In the previous cases where I was copying this 1, I didn't need to do that because that 1 was here at the center, and we know that the next element has already been scanned for because it's the same as this next element, right? But here, because we are at the end of our range, this next element is not the same as this next element, and so we cannot comment. So if we reach the end of our selection range, we still need to extend our search. So what I will do is I will extend my search. So I'll need to extend my search from this A. So from this A, I'm saying I had searched these 4, and I have to extend my search to a 5th element over here. To a 5th element over here, that is this A. And you'll see that they indeed match. You will again try, you will check, okay, does the E match this next A? It does not. So we can stop here. And so this answer is not 4, but is actually 5. I hope that made sense. Now again, for the next A, it's just 1. And remember, 1 falls fully inside this range, so we don't need to worry about it. So we'll just write 1. The next 0. So again, the 0 is fully inside the range. We don't need to worry. The next 0 is fully inside the range. Now again, when I'm copying over this 4, can I write 4 here? Obviously not, right? Because, I mean, there are only 2 characters in front. And why? Because again, the number 4 is going outside of our range. Our range was just this much. Now we need to be mindful of the fact again that this 4 is going outside of our range that we had talked about, right? This range. So because the 4 is going outside the range, we can only have certainty up till the range because I've only analyzed those elements. So I can't write 4. Instead, I'll write 1. because I know for sure, okay, this A is matching our selection A, but we don't know anything else because we haven't actually looked at these elements, right? Because if that number led to another number, led to a character that was inside our range, we can say with certainty that that number is fine. But if it goes outside of our range, we can only consider characters that is falling inside our range. So that's how we got 1. And finally, E has to be a 0 because, yeah, it does not match the beginning thing. Okay. So I did talk about that for a very long time. So let's just go through the code to actually cement what I talked about. So here L and R represent the left and right like indices of my selection range. So in this selection range, this is going to be L, and the right marker is going to be R. So this would have been L and this would have been R, right? And let's try to keep in parallel what I said before. So again, Z0 will just be initialized as N because that's what it is. And then we will loop through the elements one by one as I was doing. I will check if I is less than equal to R. So if I is less than equal to R means I is inside this range that I'd already talked about, right? If it's inside the range, then Zi, that is the number that I'm writing below, is going to be the minimum of R minus I plus 1. So this means the number of leftover elements from the right side. So remember I talked how if the number goes outside the range, we cannot consider it, right? We can only consider the total that is actually up till inside the range. So this will consider that and the minimum of that and the Z value that we copied over. So you can either consider 4 or you can consider how many ever elements are left in your range, which in this case was, in our last case was 1, and we took the minimum. So that's that. And then after that is done, we will try to extend our search. So we will iteratively check one by one again and increment our Z accordingly. So remember how in our previous case, like for this A with the 5, we had originally wrote it as 4 because that was the value that we got from Zi minus L here. We had gotten 4, but because of our while loop, we have to increment one more because it went outside of our selection range. So that accounts for this part where we try to extend our search. And finally, if we extend it past R, we'll have to change our L and R. So again, you saw how when I was extending the search from there, we'll have to extend our bound of R as well. And that kind of wraps up the algorithm. Okay, so now let's go back to actually solving our problem. Remember in the beginning, we had talked about all these, how this second, okay, now we are done with this second problem. And now we need to use this to solve the first problem again, right? So the idea is we construct the string A plus hash plus B. So let's go to an example so we can understand it. So consider this where ABD is my A string and this thing is my B string. And let's say I've already computed the Z using the algorithm from above and I've obtained these values. Okay, great. Now, obviously I'm only interested in the part with B. So I'll start by looking at the first index of B. That's going to be A. So we'll start by looking at the first element here of B, which is this one. And this has a value of 3. So remember that this 3 means that the next 3 characters match the next 3 characters here. That's what that means. But this doesn't really mean that the remaining, so as in if I remove just 0 characters, the remaining 5 characters are not going to be a prefix of ABD. So this is not a valid point, right? As in I need the entire this thing to be a prefix. Only then the full remaining part of B will be a valid, the full remaining suffix of B will be a valid prefix of A. So this is not a valid point. So let's put an X mark. Now let's look at this B. So again 0, so it's clearly not a prefix. So I'll put an X here, same for D. Now this 2 says that this AB is equal to this prefix of AB. So now this is actually correct. The entire suffix of B, if you remove the first 3 characters, is indeed a prefix of A. So this is a valid point, and in the same logic, this is a valid point as well. So here again, because we wanted to minimize the O of n square cost, we wanted to minimize the x square cost, we will try to break it into as many pieces as possible. So in my first iteration, I will remove all 3 of these. So I will incur a cost of 9, which is 3 square. Then in my next, I will remove this, which will give me a valid prefix, and that will give me a cost of 1. And again, removing this will give me a cost of 1. And this gives me a total cost of 11. And this is the best we can do. So let's quickly cover the code for that part as well. So in the beginning, we will obviously take our input and we'll compute the z values for a plus hash plus b using the same algorithm that I described before. We will just slice out the part that is the b part, because again, I did not even consider anything before the hash. I was only interested in the b part. So I'll slice that out. So this number of matched is a slice of the z vector. And I will start by maintaining my cost. And wherever I get the number of matched to be equal to the remaining length of b, that is the remaining characters left, then at that point I will simply add the square of the cost, and then we'll just maintain our remaining last I so we can compute this. And in the end, we will output our final cost, and this is going to be our answer. So let's do a quick time complexity analysis as well. So from the original code, this looks a bit messy, as in this. Okay, let's go through it. So we see this first for loop. So this is obviously just going to have O of n, as in this will iterate n times. So this entire if block is only going to be iterated n times. That's great. But this while loop seems a bit deceiving, as in how are we sure that this is O of n? So let's pay attention here. We had initialized r as equal to 0. You will notice that in the entire code, r is only being modified at this point. So r will always be incremented by zi. So this while loop will execute, let's say x, if this while loop executes y times, then r will get incremented by y, which means that, okay, this while loop can technically be as long as it wants to be. It can be O of n for one given value of I, but because r is incrementing by the total number of iterations of this while loop, the total number of iterations of this while loop will also be constrained to O of n. And because of this, this whole algorithm is also O of n. Let's have a look at our other part. I think this is very straightforward. This is very clearly O of n. There's nothing confusing, which gives us a total time complexity of O of n, where n is nothing but the size of our string that we inputted into the Z algorithm, which is the size of a plus b. And that solves our problem.
Let's see problem B, power and space. The gist of the problem is you're given an array A of size or having n elements and an integer L. You may replace any number of elements greater than some chosen x with x itself. Your task is to find the maximum such value of x such that for which the length of all subsequences formed will be less than equal to L. If no modification is required, then you have to output -1. So the first step to solve this question would be to ensure that all possible increasing subsequences are not exceeding L. We will check the length of the largest increasing subsequence. Because if the largest increasing subsequence is itself greater than L, then we do not need to check for other subsequences because we'll have to reduce that subsequence itself. And if the largest subsequence is of length less than equal to L, in that case, there'll be no subsequence with length exceeding L. In that case, we can simply print -1 and our work is done. Now, to find the length of the largest increasing subsequence, we will use the classic algorithm using patient sort of time complexity O of n log n. This algorithm consists of using a vector LIS. For each element of LIS, we find the first element in LIS that is greater than or equal to x using the lower bound. If not found, then we append x to the end of this LIS vector, increasing the length of the vector. Otherwise, we replace that element, which is the element just greater than or equal to x, with x to keep the smallest values possible. And the length of this vector finally that we'll get, it will be the length of the largest increasing subsequence. Now note that LIS does not store the actual subsequence, but a representation of the lengths. And the size of the vector at the end is equal to the length of the LIS. Let's see how to find LIS efficiently using this example. It will be more clear then. So say we have an array 3, 5, 2, 10, 6, 4, and 7. We take the LIS vector. Initially, it's empty. So we'll append 3 in this vector because there's no element to compare it to. Now we take the next element 5. Since there is no element that is less than or equal to 5 in this LIS vector, we append 5 after 3. Next, we take this element 2. Now 3 is the first element in LIS vector that is greater than or equal to 2. So we change 3 to 2 by 2. Now we take the next element 10. Since both 2 and 5 in the LIS vector are less than 10, we will append 10 to the end of this vector. We move on to element 6. Now the first element that is greater than or equal to 6 is 10. So we replace 10 by 6. We move on to 4. The first element greater than or equal to 4 is 5. We change this to 4. we go on to 7, and since there is no element that is greater than equal to 7 in this LIS vector till now, we append 7 at the end. So the length of this LIS vector at the end that is formed will give us the length of the largest increasing subsequence, and that is 4. Note, as I told before, this LIS is not giving me the actual increasing LIS subsequence, but just the length of this increasing subsequence. The actual increase LIS would be 3, 5, 6, and 7, of which is also of length 4. So LIS is just used to find the length of the LIS subsequence, actual LIS subsequence. Now moving on. Now, once we have got a method to find the length of LIS efficiently, what we need to do is we need to binary search on all possible values of X. Now, note the range of possible values of X would be from 1, which is the least possible value of each element, to max value of in the vector. Now, if we choose X to be 1, then all the elements would obviously be greater than, would either be greater than equal to 1. In that case, all elements of the vector would become equal to 1. That is essentially, we can say that we are ideally changing all the elements of the vector. And if we take X to be maximum value, that is the largest element present in the vector, in that case, there'll be no element that is greater than this largest element in this vector, and no value is thus being changed. Hence, we can say that X is ranging from 1 to max value. So we will binary search on all these possible values of X. For each mid value that we get, we will change the array correspondingly. That is, all elements that are greater than X, we will replace them by X. And then using our LIS function, the way that I described before, we'll compute the LIS of this new array. Now, if we get the LIS to be greater than L, now in that case, this means that the largest increasing subsequence has more elements than required, because the length should not be exceeding L. In that case, what we need to do is we need to decrease our value of X, so that there'll be more elements that are greater than X that could be changed to a same value of X, and thus essentially decreasing the overall length of the LIS. So therefore, we'll change our high to mid -1 and move on. If the length of the LIS is less than equal to L, in that case, now the mid that we got is already one value of X that is acceptable, since that was what was required by the question. However, since we need the maximum value possible for X, we will update low to mid +1, and we'll also check for higher values if there are more values of X that we can get. Now, this is the, just a moment. This is the code implementation for the question. This is our LIS length function. In this function, this is the LIS vector. For each value in the vector A, we first check for the first element that is greater than equal to this value val element in this vector. If there is no such element and the iterator is equal to the end of the vector, in that case, we push back this element, this value into this LIS vector, thus increasing the length of the LIS. If we find an element that is greater than greater than equal to val, in that case, we replace val by we replace this element by val. And finally, we return the size of the LIS vector, which will give us the length of the in LIS consequently. Now, firstly, so for the first array that we got, we find the max value, that is the largest element present in this vector. This will be the highest possible value that our X could have. Now, we first find the original LIS value for this given vector A. If it is less than equal to L, then no modification is required, and we can simply print -1 and move on. However, if the length is greater than L, in that case, we start binary search. We take the lowest possible value for X is 1, as I explained before, and the highest possible value is max val. Initially, we'll keep answer to -1 because we haven't calculated any value of X till now. Now, while low is less than equal to high, we'll calculate mid. we'll take a new vector modified, and we'll change this vector A as per the specifications of the problem, that is for all elements that have value greater than mid. So those elements will be changed to mid. Now for this new modified vector, we'll find the LIS for it. If the LIS is less than equal to L, in that case, mid is one possible value of X that could be there. So we update answer with mid, and we change low to mid plus 1, and we continue this binary search to find if a higher value of X is possible. Otherwise, if the length of the LIS is greater than L, in that case, we have to go lower. So we change high to mid minus 1, and we continue this loop. Finally, we print the answer. The time complexity for this solution will be O of log of max val into n log n. This is because binary search of X is from 1 to max value. So its time complexity will be log of max val. And for each binary search, we are first computing the LIS value. We are first finding the lower bound, and then for every element, we're first finding the lower bound and then updating. So finding the lower bound is log of n. And since we are doing it for each element n, the overall time complexity is n into log n for one particular binary search. So overall time complexity is log of max val into n log n. And this is pretty efficient to solve a question.
Hello, let us now solve problem E from mock internship test 4, complications. So, here Paja thinks that normal functions are too simple and he came up with a new one, complication, and he defines complication as follows. We consider each place units, tens, hundreds, thousands and so on separately, and for each place we compute the value of s by adding together all the digits which occur a number of times, that is a multiple of d itself, right? I will explain this with an example. Now, consider these three numbers: 12, 31 and 999. Okay, now what do they mean is, for each place, say the units place over here, we have 2, 1 and 9. We calculate the frequency of how many times each digits occur in that particular place. So for example, here 1 occurs 1 times, 9 occurs 1 times, and 2 also occurs 1 times. So, and we add to s the frequency of the digit d, that is a multiple of d itself, right? Meaning we add this one because 1 is a multiple of the frequency with which it occurs, which is 1. So we add 1 to our answer. And also we add the digits except 2, 9, because they, like for example 3, 4, 5, 6, they all occur 0 times, and 0 is a multiple of d, as told to be considered here. So we add those digits as well. So like we add 3, 4 and so on. So our answer for s in this case would be 34. 45 minus 11, so it would be 34. And now that's how we calculate s. And now the question further says that we concatenate all the values of s from left to right, and we ignore any trailing zeros in s while concatenating, and this is the final complication of the sequence, right? And we need to find the complication of a sequence for q queries of the form LR, and we need to find the complication of the particular subarray, right? AL to AR, L and R are included over here. Okay, so how do we go about solving this problem? Now, consider this over here. What we do is, for each place value, we maintain a frequency array of 10 digits, like from 0, 1, 2, 3 and so on. We maintain a prefix frequency array for each digit, right? And then as we move along the n values over here, we add 1 to our previous value if that current digit is what we require it to be. Like for example, here this digit is 2, therefore the value of the prefix array, prefix frequency array at index 1 would be 1, and the remaining all will remain 0. This is how we update stuff, and then at the second index this will also become 1 and this will remain 1, and this will 0 0 0 and so on. This is how we maintain a prefix array. And then now when we have our prefix array and we know our ranges L and R for each q, we maintain a array called answer, where we store the complication and update it as we go along the places from the rightmost ones place to the most significant bit place. And then yeah, now for each L and R we use the prefix difference, like pref of R minus pref of L minus 1 to get the frequency of a particular digit in that place. And now once we know this frequency, we check if it's a multiple, and then if it's a multiple we add it to our sum S, right? And yeah, um, for each q we maintain a separate answer array. There we update our current total complication, and then as we iterate over that we update using this, and then that's how we arrive at the answer. Let me explain a bit more clearly with the code in mind. Also note here, before we go into the code, note that the value of AI is from 1 to 10 power 9, so, and it's less than 10 power 9, so there are at most 9 digits in a number. Okay, now, with this knowledge let us dive into the code. Alright, so check this out. I'm getting the inputs over here, and then I'm maintaining vi. Here vi is a vector of long integer, and yeah, so like we need to store a big value, so we are using a long. And now we initialize answer array, and we store the query, right? So we need two arrays for that as well. Now what this mult essentially does is, I'll explain as we go along, but this essentially is used for the updation of our answer array. Alright, so for each digit we noted that there are only 9 digits possible, so for each digit for each place value from the rightmost to the most significant digit, we store a prefix array, and we store a presence array, which is basically a type of flag whose use I will say later. Just note that we have uh, used a presence array over here. And yeah, so what we do here is, if a number is non-zero, we update the presence array. So what basically this does is, the approach over here is to get the least significant digit at every point, and then update the original array itself, because we won't need that anymore, and we update the prefix frequency array over with this. And then yeah, we update the element aj by dividing it by 10 and taking modulus with 10 to get the digit, and then yeah, updating it. And so what we do is, if a digit is if a number at some point becomes 0, then there won't be any presence of it in a particular digit, right? So say for example, we have three numbers, 29 and 30 and 31, say. So for the hundreds digit, there won't be any presence of any elements in the hundreds digits. So the presence array will remain 0 throughout, and we need not append anything to our answer array, right? So that's the purpose of this um, presence array. So now for each number in the AI we do this, and we update the prefix frequency array. No, for each query, what we check is we check if there is a presence of a digit, like at least if some number in that place value is non-zero, so that we proceed further, or otherwise we continue if there's no such digits, because our job would then be done for that particular query, right? There might be some other number outside the range of the query, um, for which such a place such a digit is non-zero, but within this query if it's 0 we just continue and we move on. Now for we initiate sum to be 0, and then we keep a flag to check if at least one of a digit in the prefix frequency is non-zero or not. If there are no digits which except 0 which has a presence, then our sum would become 45. Let me explain what is happening. Okay, so see, say we have three numbers, 101, 1001, and 100. Okay, now in the tens digit we have three zeros occurring three times, and the remaining digits occur 0 times. So our sum should be 45 instead of 0. That's why we use the flag. Okay, and we check if the flag is not that and presence is there. That means that before this 0, that is towards the left of this 0, there is at least one non-digit number. Therefore we have to consider this place value as well, and therefore we update our sum to be 45, right? Now here comes the use of the mult array which we are storing, which essentially what we need to do is we are, say we have some x y z as our answer for the particular query. What we need to do is we need to append the answer for the current place value towards the left over here for that particular number, right? So what we do is we have store a multiplier. We multiply this number which we obtain as sum by that multiplier, and then add this xyz, so we get a new number and store it to our answer, right? That's the point of the multiplier. Hence what we do is if the sum is 0, we do not change anything to the multiplier, and if the sum is a single digit number, we multiply the multiplier by 10. Otherwise we multiply the multiplier by 100, right? Ignore this bit. Yeah. So that's how this works, and that's the use of multiplier as well. And in this way we keep on appending our answer towards the left for each place value from the places 0 to 9. That is for the 9 digits, which is the maximum number of digits possible. And now at the end, for each query we output the answer divided by the mod, which is 1e9 plus 7 as mentioned in the question, right? Now I hope you understood the solution. Now let us understand the time complexity of this solution. All right, so let m denote wait a minute, max number of digits. Then for each digits we iterate over all numbers once, and then we for each query as well we iterate over all the queries, right? So basically our time complexity would be order of m into n plus q. This will be the overall time complexity of our solution. I hope the solution is clear. Please give it some more thought as well if it's not clear. Thank you.